Good afternoon. Um, Welcome to day 21 of 28. Okay, so sometimes I'll give lectures where I'm not happy with the quality. Last week was one of those examples. Not last week, last class. Now it's a difficult, this part of the course is difficult to teach. I'm gonna try my best to try to get more of the content from my brain into yours than last time. The best way to grasp first and second order circuits is to try to work through yourself, really, on your own time, and just try to, starting from first principles. And first principles in this case can mean initial condition, final, solve for each of those, and then plug it into the general form of the solution. And hopefully today we're going to start off with RL, first order RL circuit. So that's a circuit that has one inductor and a bunch of resistors in it. And hopefully, because you've been exposed to RC first order circuits already, it will kind of help you wrap your head around RL circuits. Again, I'm going to try to unpack the material and present it in a digestible way. Okay, so here we go. So first of all, step response. So there's two types of circuits that we're considering in lecture 7. There's RC circuits and RL circuits. And then there's two types of conditions that we're working with. Condition number 1 is source free. So what that really means is that there's a source that's connected to the circuit, and at time 0, it's disconnected. And the capacitor voltage or the inductor current doesn't go to 0 instantaneously. It takes a while for it to decay back down to 0. And that's what we're solving for when we look at source-free circuits. Now, step response is kind of the other is kind of the reverse. The circuit is not connected necessarily to a source leading up to time 0. And then at time 0, we connect a battery or a current source to it. And so we then monitor the time course of the capacitor voltage, and in this case, the inductor current. So this is a good picture to focus on, to see what's happening. You have an inductor that is sitting kind of idle. This switch goes from the open position to the closed position. So I can. Okay, so at time, can you guys see my PowerPoint?
Yeah.
Yes, no, so. Okay. Yes, okay, you saw it. Did you see just the slide, or did you see the whole presenter view? You can type in the answer. I'm looking at the chat now. Only the size. Okay, good. So I'll go back to it. Okay, so you have an inductor, okay, and before time zero in this circuit, you can see that there's no current flowing through this inductor. Why? Because the switch is open and there's no path for the current to flow. Now at time zero, this switch is going to close, and all of a sudden there's going to be a current that flows from the battery through the resistor, through the inductor, and back to the battery. Now here's the thing, at time equals what, after long enough has passed, this inductor will converge into a short circuit. And then when this is converted to a short circuit, then it's just like a circuit with a battery and a resistor in series. And then a current flows like that. However, we are very interested in that transient current. So what happens right after this switch is closed? And so what we saw last time with RC step response was that our solution has two parts. Okay, part one is what's called the forced or steady state component. And so what I just said, when this thing is a short circuit, when enough time has gone by for the transient to die out, then a current of Vs over R will be flowing through the circuit, including the inductor. So right away, I'm just going to tell you that the value of IF is equal to Vs over R. Now, IN is going to have a transient form, so it's not going to be a constant. IN is going to be an upwards, an ascending exponential function. And so the value of IN, so IN starts at 0 because at time 0, there's no current through the inductor. And it's going to kind of ascend exponentially up to its final value. Okay. So let's try to figure out the value of IN. And so we know that it's going to have, the general form where A is the initial value and tau is a time constant. And we saw from previous lectures that for an RL circuit, the time constant is equal to L over R. And A is some constant that we don't know yet. So we have to solve for A and tau and IF. So the force response we know. So like I said, it's Vs over R. And the way we know that is at time equals to infinity, this thing is a short circuit. And so our circuit just has a battery with the voltage of Vs in series with a resistor. So the current by Ohm's law is Vs over R, and that just flows. Okay, so we know the value of IF, but we need to find the value of A and tau. And we're going to get that by applying the principle of continuity to the inductor. And so remember we said that for an inductor, its current cannot change abruptly. And so even when there's an abrupt change in the circuit, such as this switch going from the off position to the on position, that current cannot change abruptly from, basically, and we know that the initial value is going to be 0 because before time 0, this inductor was not connected to anything. So it's just a dead circuit before time 0. And because of continuity, its value precisely at time 0 is also going to be 0. Okay, so if you combine, if you substitute this equation into here and this equation into here, then you get the following form. Okay, so again, this is the part of the solution that is always there, right? And this is the transient. So our job is to find the initial condition of the constant A and the time constant tau. An inductor has to obey continuity of current. So the value of the inductor current right after time zero has to equal to the value of the inductor right before time zero. This equation is a statement of continuity. And so at time zero, when you plug in 0 for t, we know that the value of the current, which we're going to call I naught, is equal to A plus Vs over R. Okay, so how do we get from here to here? Well, we plugged in I naught just as a variable for the initial current. And and we substituted in 0 for t. And that just leaves us with A plus Vs over R. All right. And so in other words, A is equal to I naught minus Vs over R. Very straightforward. So now if you substitute in the value of A into here, you get this form. So all I've done is I've rearranged to solve for the constant A, figured out that it was I naught minus Vs over R, and I've plugged it into this term. So this can be written as I of infinity, that's the force term, plus I naught, the initial value of the inductor current, minus I infinity times R decaying exponential. And so in this special case, okay, so let's just draw a picture, which may make it better. So let's say that our current starts out at a positive value, a non-zero value, which we're going to call I naught. We know that it has to eventually converge to a value of Vs over R, right? So over time, it will slowly but surely decay or converge to a terminal value of Vs over R. So I infinity is Vs over R, right? And so this is the case where the inductor has some initial current flowing through it. So sometimes I naught will be 0, in which case this curve will be kind of inverted. It will start out at 0 and it will climb to Vs over R. Okay, so here's your recipe for solving for the RL step response. First, find the initial inductor current. So in other words, solve the circuit at t equals 0 minus, and then use continuity to carry forward that solution into t equals 0 plus. Step 2 is to solve the circuit at time equals to infinity. So at time equals to infinity, the inductor is just replaced by a short circuit. And step 3 is to find the time constant. So that is obtained again by looking from the inductor's point of view and measuring how much resistance it sees. Okay, so let's and a couple of other notes here. If the switching happens not at 0, but at time t naught, then you use the same general formula of solution. You just shift time by t naught units. Right? So you replace t with t minus t naught. Now the special case that I was alluding to, when I naught is equal to 0. So in other words, when the inductor starts out not carrying any current, then this term becomes 0, and you can factor out the Vs over R. So Vs over R is the value of I infinity. So you can factor that out and get this form, right? So when time is equal to 0, be 0. So it starts out at 0 and it climbs to a final value of Vs over R. So those are the steps for solving for RL step response. Before delving into the examples and practice problems, I will just say a few more things, namely the voltage. So first of all, for an RL circuit, you want to first solve for the inductor current. Once you have the solution for the inductor current, you can use L times I prime to get the inductor voltage. And so always in an RC circuit, solve for the capacitor voltage. In an RL circuit, you want to solve for the inductor current. And once you have the full solution, and use it to solve for the other circuit variables. Okay, so if you take this solution and differentiate it, multiply it by L, then you get this form. In other words, the voltage is equal to big V of S, that's the battery voltage, multiplied by the value is 0 up until time 0. Okay, so again, the picture I think is very helpful. So when the inductor current starts out at 0, and it needs to end up at Vs over R, it's going to take this exponential or logarithmic ascent from 0 to its final value. On the other hand, its voltage is going to start out at Vs, right? That's the initial voltage when the battery first gets connected, and it's going to end up at 0. This is when it becomes a short circuit. So in this picture, right, when this battery is first connected, there's no current flowing, and the inductor senses all of this voltage. And as time goes by, the inductor has less and less of a voltage until it finally becomes a short circuit where it has 0 voltage, right? So whereas the current starts out at 0 and ends up at Vs over R, the voltage starts out at Vs and decays down to 0. Okay, so that kind of hopefully gives you a little bit of an intuition as to what's happening in an RL circuit. It's just really the derivative of that. If you differentiate this curve, you'll get something that looks just like this. All right, let's work through some examples. So in all of these, we're going to be asked to solve for I of t. And I of t is always going to be defined as the current through the inductor. Just see something. I want to make sure that I don't. Hopefully, when I'm in presenter view, it will still show me the chat. If there's any chats. Okay. Our first example, and I'll work through this one, and then I'll ask for your help for the subsequent problems. The first thing that we need to do is to solve for this circuit at time equals 0. Okay, so you know what? Let me actually switch back to this view. Oh, it's not great either. I know what I'm going to do. I'm going to disconnect my external display. Okay, let's try this again. Okay, so at time, so before this switch, before this switch, so at time equals 0 minus, this switch is in the closed position. So we have, this is connected. So when the switch is closed, what happens to this 3 ohm?
It short circuits the amp resistor.
That's right. And remember also that at time equals 0 minus, the inductor is also a short circuit because it's been sitting there for a very long time without any change, right? So how much current, I lied, I said I'm not gonna ask for help. I'm gonna ask for help for this first one. How much current is flowing through the inductor when this switch is closed and when the inductor is a short circuit? Five. Excellent. Oh, a bunch of answers. That's awesome. You're all correct. It is 5, absolutely 5, right? Because we have, oh, okay. So the value at time equals 0 minus is 10 volts divided by 2 ohms, right? Because this, when this is connected, when the switch is in the closed position and the inductor is a short circuit, then we just have 10 volts and 2 ohms, and that's it. Just a simple series circuit. So 5 amps is flowing through the inductor at 0 minus, which means that 5 amps is flowing through the inductor at time equals 0 plus epsilon because of continuity. So we have our initial condition. The next thing that we need is to look at this. Well, there's the answer, but let me now explain what happened. How come now I'm including the 3 ohms? Well, because the time equals to infinity, this switch is in the open position, right? And so you have a 10 volt battery, a 2 ohm resistance, and a 3 ohm resistance. So you add these two, and you get a total resistance of 5 ohms. Again, at time equals to infinity, this inductor will be a short circuit. So you just have 10 volts divided by 5 ohms, which is 2 amps. In other words, the inductor current starts out at 5 and ends up at 2. So the last thing that we need to solve for is how quickly does it go from 5 to 2? And that's the time constant. So for the time constant, what we're going to do is we're going to short circuit the battery. We short circuit any, we're going to short circuit any independent sources, right? So this becomes a short. And this switch will be in the open position because we always look after time 0. And then we look from the point of view of the resistor, how much resistance does it see? Well, it sees the 3 ohms and the 2 ohms in series, right? So it sees a total of 5 ohms. And so its time constant is 1/3 henries divided by 5 ohms. So in other words, it's 1/15 of a second. So now we have all 3 ingredients of the solution. We have the initial condition, we have the final condition, and we have the time constant. And let's plug those in. So the steady state solution is 2, and the initial condition is 5, and the time constant is 1/15 of a second. So dividing by 1/15 is equivalent to multiplying by 15. And so our final solution is 2 plus 3 times e to the negative 15 t amps. Okay, so I'm gonna stop here for just a second and I'm gonna let you guys ask questions if you have any. All right.
Professor, can you explain why we included the Professor, can you hear me?
Go ahead.
Can you explain
Yeah,
why
I can
we
hear you.
included the 2 and the Can you explain why we included the 2 and the 3 ohm for when current goes to infinity?
Oh, when time goes to infinity?
Yes, when time goes to infinity.
Yeah, so so when time so when time goes to infinity, then the circuit then the battery is still there, right? And the 2 ohm is still there, and this switch is in the open position, right? So the circuit looks like this. Looks like that. This is the 2, and this is the 3, and I is defined here, right? Because this
Okay, so it
this
stays
switch is
as
in the
a
open position.
switch.
So all of the yeah that's an important it's important that that's understood, that this notation means that at time 0 the switch goes from the closed position to the open position and it stays there.
Okay, thank you.
It's more of yeah, you're welcome.
Professor, just letting you know, you're cutting out a little bit.
Yeah. Yeah, it's giving me the message that my internet is unstable. Let me see if I can. This never happens. I rent an office here that is supposed to have good internet, but let me I'm gonna stop my video and hope that it helps. Can you guys hear me now? Okay, good.
Yeah,
Hopefully that
it's
will help.
better now.
Otherwise, okay. Yeah, I'm gonna try. Otherwise, I'll restart my computer. I've never had this problem before in this office. Hopefully it will not persist. Okay. So yeah, the arrow means that at time 0, the switch goes from the closed position. So when it's in the closed position, we bypass the 3 ohm resistor. But when it's in the open position, then then the 3 ohm resistor is now connected to the battery. All right. I'm gonna move on. I'm gonna go slowly because you know, I really don't want this to go over everyone's head. Okay. So let me move this out of the way. I'm mostly doing this for my sake. It's distracting for me to have the solution there. All right. All right. So in this circuit, first of all, we are asked to find the current flowing right to left across the inductor. And we have a current source that is always on. However, this part of the circuit goes from the closed position to this switch, goes from the closed position to the open position at time 0. So what I like to do in these is, and you're going to be doing this a lot. You're gonna draw the circuit at time equals 0 minus. Looks like an emoji. Okay, and we're going to draw the circuit at time equals 0 minus. So right before this switch opens. So before the switch opens, right, and the inductor is a short circuit because nothing has changed in the circuit for a long time. And 10 ohms. And how much current? So how much current is flowing in this branch here in this circuit? Which is an interesting problem. I like problems like this. So basically, the 3 amps will come out here, and it has 3 paths to choose, right? It can either to return, basically you should think of this picture as following. The charge comes out of this end, goes over here, and it has to find a path back to the current source. So how much of that current? Yes. Yeah. Omar, you're correct. All the 3 amps. That's right. All the 3. And the reason is that the path that the current is going to take, and this is one of the only advantages of teaching online, is I can use different colors. The current is going to take this path. Because there's no resistance here. And therefore, all of the 3 amps is going to take this path. And so okay. So that's step 1. So now let's draw the circuit at time equals to infinity. So at time equals to infinity, this switch will be open, so we can ignore this part of the circuit. And so the circuit will have, oh, let's not do that. We have the 5 ohms. We have the short circuited inductor. And the current source is still there. Okay, and the current that the variable that we're solving for is this current I. Okay. So my question to you is, how much current takes this path? So I'll give you a hint. Yeah, I even need to give you a hint. The answers are coming. You guys say 2 amps, and that sounds correct. Both of you are correct, right? So it is absolutely going to be 2 amps because of current division. So by current division, I am just going to call it I5 is equal to I is equal to 3 times, right? 10 over 10 plus 5. I like that. So 2/3, 2 amps, right? And that is equal to the I of infinity. Okay, so in this picture, we have a current divider with 10 ohms on one branch and 5 ohms on the other branch. And so the 5 ohm branch has 1/3 of the resistance. And so it will carry 2/3 of the current, which is 2 amps. Okay. And then the last thing, the last part of the solution is to get RTH. Draw circuit at time equals 0 plus for that. So let's draw, and we're going to be looking from the point of view of the inductor. So and remember that we open circuit any independent sources. So we have a 10 ohm resistor here and a 5 ohm resistor here. So we are looking there. We're looking from the point of view of the inductor. And so remember that at time equals 0 plus, this is going to be an open, the switch is open. So this is, right, so basically all we have is this path here. So what is the value of RTH in this picture? Let's see what the audience says. 15 ohms, excellent. Ah. Okay, so put in my text box. Which makes our time constant tau is equal to L over RTH is equal to 1.5 over 15 is equal to 0.1 seconds. Okay. Get rid of this. Okay, so now we have everything. So now let's write our final solution. Right. So we have I of t. And so I of infinity, we found out was 2 plus and hopefully that is the correct answer. What did I get wrong?
Wasn't I not
Oh,
3?
oops. Yeah, sorry. Yeah, I just made a typo. Thank you for that. Oh, I guess I have to retype it. Zoom doesn't, it seems to. So let me just type it again. Right, so this is our natural response that I'm typing here. That's equal to 2 plus 3 minus 2 times exponential negative 10t equal to 2 plus exponential negative 10t. And that's our final answer here, this thing. Right, and so this is valid for time to 0. So it starts out at 2 and it rises to a final value of 3. So basically, when the switch is in the open position, or sorry, it starts from a value of 3 and it ends up at a final value of 2. So before this switch goes from the closed position to the open position, all 3 amps are flowing through the inductor. And once it opens up, then all of a sudden, some of the current starts flowing through the 5 ohm. And that's the change that occurs. And the inductor current, or some of the current starts flowing through the 10 ohm. And so the inductor current goes from 3 to 2. All right, hopefully you're able to follow that. I'm going to skip number 3 because the solution is in there. And I'm going to do this problem. I'm going to put aside the solution. Yeah. Okay. So this is one of those pesky problems where we have 2 switches. So whenever you see this, and if it starts to cut out, if you guys lose me, just send me I was gonna say send me a chat, but you may not be able to. But if I really start to cut out, let me know and I'll restart my computer, hopefully get a better internet connection. Okay, so we're gonna need to solve this problem. We're gonna need to solve this circuit at multiple time points. Right? So basically, you have the first switch that occurs at time 0. And we need to know what happens right before, we need to know what the value of the inductor current is right before that first switch flipped. Then the second switch happens at time equals 2. So we need to know exactly what was happening to the inductor current right before that second switch flipped. And then finally, we need to know when long after both switches have been closed, how much current is flowing through the inductor. To solve this circuit, kind of 3 separate time instants. And I will try to demonstrate how to go about solving these problems that have multiple switches. So let's draw this circuit at time equals 0. Okay. So at time equals 0, this switch is open. And so it's kind of straightforward, actually. You have your current source. And then you have this. Right, so the inductor current in this picture has to be equal to what? What is the value of the inductor current in the picture that I've just drawn?
Zero.
It will be 0, exactly. Because there's nowhere for the current to go. right? That's the value time equals 0. Okay. So let's now draw this picture at time equals 2 minus. So right before, so after this first switch is closed, but before the second switch has. So let's again draw this picture. And now this switch is closed. And we have the 10 ohm resistor. And we have the 20 ohm resistor. And we're going to pretend, we're just going to assume that 2 seconds is long enough for that first transient to die off, such that the inductor has basically converged to a short circuit. So what is the value of I in this picture? So remember that the value of this current source is 6 amps. So we're going to use current division. And the question is, how much of that 6 amps takes the outside path and flows like this?
Two.
2. And how did you get the 2? What was your fraction? What was in the numerator and denominator of your fraction?
15/30.
Excellent. That's it. 15 over 45, right? 15 over 15 plus 30.
Yeah.
And so that's right. This branch, notice it has 2/3 of the total resistance. So it will carry 1/3 of the total current, which is 2 amps. All right. And so I at 2 is equal to 2 amps. All right. So now we have initial, we have the condition kind of after, right before that second switch flips. And now we need to draw the circuit again at time equals to infinity when both switches have closed. So let's draw the circuit one last time. Okay. Oh, I guess I'll put it in. This is 15. This is I. So now what is the value of I in this picture? This is 6. Times what? What's going to be in the numerator and what's going to be I'll give the numerator will be the same. It will be 15. But what will be, let's see. Yes, 3.6 amps is correct. I believe is correct. Seems very familiar. And it will be, try it again. is equal to 6 times 15 over 15 plus 10. So that's 60% of 6, which is 3.6 amps. All right. So now we have our initial, final, and kind of second initial condition. You can think of this as a second initial condition because we have two transients here. So now we need to find the time constant. So to get that, we basically we need to determine how much resistance is seen by this inductor right after the first switch flips and right after the second switch flips. Try this erase function. This is cool. I wanted to leave I'll just write it again. So I'm going to write down what we know so far. Okay. And now we're going to solve for RTH at time equals 0 plus. We're going to draw the circuit after disconnecting all the independent source. So we're going to look from the perspective of the inductor, right? And we're going to see the 20 ohm. We're going to see the 10 ohm. Right, and I'm going to draw this switch open. And I'm going to see pardon the handwriting here. So this inductor at time equals 0 plus, so right after the first switch flips, we'll see the 20 ohm, the 10 ohm, and the 15 ohm. And so the RTH is going to be equal to 45 ohms, which makes tau is equal to L over RTH is equal to 1/9 seconds. Right, because the inductance is 5 and our RTH is 45. Okay, so now let's repeat for our RTH at, excuse me, 2 plus. So right after that second switch flips. So let's again draw this. Oh, we have a chat. Between the 15 and the 10. Let me just take a look. Yeah, so this, I had it drawn as closed because this was a time equals 0 plus, right? You always calculate the impedance after the transient. So after the first transient, I just drew this as a connection because this first switch, S1, was closed at time equals 0 plus. So now we're looking at time equals 2 plus. So both of them are going to be closed. And so my picture is going to look a little bit different. Okay, good. I'm happy. I always like it when people understand after the fact. Okay, and now we're gonna ignore the 20 ohm here because this second switch will bypass it. And so we have 10 and 15. Okay, so the RTH here is equal to 25 ohms, which means tau is equal to L over RTH is equal to 5 over 25 is equal to 1 over 5 seconds. So it's the time constant is different in this case. All right. So here's the thing, and these are some of the this is one of the more challenging problems in the entire course. So don't beat yourself up if you're not following everything that I'm doing right now. We have all the ingredients now to the solution. But we do need to put them together. And so to put them together, what I'm going to do is I'm going to write out the 3 segments of the solution. So there's the time between, let's see, there's the time between 0. There's the time. This is the way. So these are the 3 segments in the solution. So before time equals 0, IT we saw was equal to 0 amps. Okay. Okay, so there was nothing energy before that first switch flipped. There was no current flowing to the inductor. Okay, so what about between time 0? So after that first switch flipped, but before the second switch flipped, where we know we're going to use our basically what we're going to do is assume that this was the final condition, even though we know that it's not. We're just going to assume that the steady state solution was the one that was reached when that second switch flipped. So we're going to assume. Okay. And so this was equal to, let me try to extend this. So I of 2 we determined was 2. That's going to get added to 0 minus 2. So we're going to minus 2 negative t over so negative 19. Right? Because this value here was 0. This value here was 2. And this first time constant was 1 over 9. And finally, there's time after 2 seconds. So after that second switch flipped. So here we can use our, our standard general form directly. So the second time constant was this one here, the 1 over 5 seconds. So the initial, so actually, And our initial condition here becomes the value right before that second switch flipped. So right before the second switch flipped, the amount of current through the inductor was 2 amps. So that becomes our initial condition for the second transient. So that becomes 3.6 plus 2 minus 3.6 exponent negative 5t. T minus 2. All right, so let me just unpack what I just wrote, okay? This is the final condition. This is the value of the inductor current at time equals to infinity. Now, the reason that I'm using I of 2, and this should be minus 2. So remember we said before that if the switch happens at a time later, at a time other than 0, we have to delay the natural response by however many units after 0 that transient actually occurred. So this switch flips not at time 0, but at time equals 2. And therefore, our transient response is also delayed by 2 units. So basically, if you think about the second switch, that second transient, separately from the first, right? You have your initial value of 0. That first switch flips, and the current goes from 0 to 2 with a time constant of 1/9 of a second. Halt everything there. The next thing that you do is you pretend that that value of 2 is your initial, is now your new baseline. So this is your new baseline for the second transient. Okay, so when that second switch flips, the current's going to go from 2 amps to 3.6 amps with a time constant of 1/5 of a second. And so everything's the same except for 2 things. One, our initial condition is the value of the current at time 2, not at time 0, because remember, we're using that as our new baseline. And the second ingredient, the second piece that is different here is that whereas, the general form, and I'm going to just go to the previous slide to kind of illustrate this. Oops. So where was it that it was written? Okay. So this is the relevant equation here. So if the switching takes place at time t equals t0, then you have to update your general form. So your initial condition is not time equals 0, but rather time equals t0. And you have to shift the transient. And so I think the best way that I can think of to kind of draw what this solution looks like. And so the solution is going to be in your slides. And I'm just going to try to sketch out what this looks like on a curve. Maybe. So if you have the time axis here, so this is t in seconds. This is I of t. And so we have some critical points here. So we have the first switch that happens here at time 0. And we have the second switch that happens at time 2. And we know that our final value has to be 3.6. So the current doing my best here to draw a dashed line. The current has to reach this value eventually. So it starts out at a value of 0. And at time 2, it gets to a value, draw another line here. At time 2, it reaches a value of 2 amps. So basically the curve will look like something like this. It will kind of exponentially decay here. And then when that second switch flips, it will exponentially ascend up to here. So we really have this, and the way this would actually kind of look like an S shape. So I'll try to draw with a little bit better fidelity here. Let me try to draw it in red. It's going to ascend up to 2, and then it's going to keep going after 2. Right? So it has this kind of, it has the initial transient from 0 to 2, at which point it plateaus at a value of 2 amps. And then when that second switch flips, we have our second ascent back to a final value of 3.6. All right, so like I said, this was one of the more challenging problems in this course. So just kind of, the best way for you guys to wrap your heads around these problems is just to try them yourself and try to convince yourself that this here really is the solution. All right, I'm going to shut up on this problem and I'm going to move on to another part of the lecture, and that is combining first order circuits with op amps. And inductors are pretty large, pretty bulky, and so they're not often combined into integrated circuit packages with op amps. And so in all the op amps that we're going to consider in this lecture, we're only going to work with resistors and capacitors. So we're going to work with the RC circuits. And so where can the capacitor go into an op amp? Well, it can go into 3 places. It can go in the input, in the feedback channel, or in the output. And so we're going to consider all 3 of those cases. And so, as we mentioned before, inductors are not used in op-amp circuits because they're large, they're bulky, they can be miniaturized and still give appreciable value of inductance. So we're just going to consider capacitors here. And so the basic tool that we're going to work with is nodal analysis. And sometimes we will use the Thevenin theorem to kind of redraw our op-amp circuit in a way that makes it easier to identify the Thevenin resistance and the open circuit voltage. Okay, so and the 3 cases that we're going to consider are with the capacitor on the input path, the output path, or the feedback loop. All right. So let's consider our first circuit. So this is an example where you have a capacitor connected in series with a resistor to the inverting input of the op amp. Okay, and very importantly here, we've been told that the initial value of B is equal to 3 volts. Right, so this is a big piece because we basically only need to know the initial value, the final value, and the time constant. And so we're given the initial value, and what you'll see in a second, that the final value is going to be very easy to deduce. Okay, so let me just get my cursor back. All right. So let's do nodal analysis at node number 1 and node number 2, actually. So at node number 1, basically we have that this current is equal to this current, right? The current flowing into node 1 has to equal the current flowing out of node 1. So the current flowing from this point to this point is 0 because this node is grounded, minus V1 divided by R1. And the current through a capacitor is equal to the capacitance times the derivative of the voltage V. And so minus V1 over R1 has to equal to CV prime. Okay. And we also know that V2 is 0 because of the ideal op-amp assumption. Okay. And therefore, right, so I'm gonna do my best to annotate this without losing my cursor, but basically this node here is sitting at 0 volts, and this node here is also sitting at 0 volts. And therefore, this node is sitting at V volts, right? Because 0 plus V equals to V, right? From this point to this point, we have a voltage rise of V. And I know that what confuses a lot of people here is all the different Vs. There's V1, there is V2, and there's V, and there's V naught. So just try to keep it all straight. So V is the thing that we're interested in, and it corresponds to the voltage across the capacitor. All right. Next step. So we basically, all we've done is we've replaced V1 by V, right? So the voltage here, this V1 is just equal to the capacitor voltage because this node is grounded. And so we plug in V for V1, and then we rearrange the terms. And we get the same thing as before, namely a first order differential equation, a first order ordinary differential equation to which we can easily pose a solution of the following form. So in other words, you should be able to verify that if you plug in an exponential function into V, that you will always be able to find a coefficient V naught and tau to satisfy this equation, where tau is equal to the product of R1 and C. Okay, so the form of the solution for V of t is a decaying exponential with a time constant of tau and an initial value of V naught. And notice that we know the initial value of V naught is given to us by 3. Okay. And we know the time constant is just the product of R1 and C, which in this case is equal to 0.1 seconds. And so we know that V of t is equal to 3 times e to the minus 10t. So that's the solution for the capacitor voltage V. Unfortunately, we are asked to solve for V naught, which is the output voltage. And so we somehow have to convert the voltage over here to the voltage over here. So one thing to note in this circuit is that there's no sources, right? So this is a source-free first order op amp circuit. And so we can easily apply KCL at node number 2. So in other words, the current flowing from node 1 to node 2 is equal to the current flowing across the feedback channel. Why? Because there's no current flowing into the op amp. So any current that makes it to this point is going to be guaranteed to take this feedback path. And so we know that the current from 1 to 2 is equal to C times the derivative of the capacitor voltage. And we know that the current flowing from node 2 to the output is equal to 0 minus V naught over RF. Okay, so once again, we can rearrange this and identify that V naught is equal to the product of RF and C with a minus sign times the derivative of V. And we have a form for V, right? We already solved for V of T. So we can just differentiate this expression and substitute it into here. And when you do that, you get that V naught is equal to 12 times e to the minus 10t. All right, so I'm not super confident that many of you absorbed that, but I'm just gonna proceed as I usually do in this part of the course. This is one of the most hated parts of the course, the first order op amp circuit. So what I'm just gonna do, I'm gonna skip the alternative method. I don't think it's helpful. I don't like this solution at all. So I'm just, and it leads to the same answer as before. So I'm just gonna skip it. All right. So we have, yeah, so here I'm just going to try to annotate over this. And I'm going to first define what the problem is. The problem is to find V naught, given that the initial value of this capacitor voltage here is equal to 4 volts, right? So the first thing as always is to find a solution for V of T. So notice that this is 0 volts, which means that this is 0 volts. So V naught is the voltage between this node and ground. And V is the voltage between ground and the output. So right away, we can easily identify that V of T is equal to negative, or another way of phrasing this is V naught of T is equal to negative V of T. So in other words, if we find V of T, then we can easily solve for V. Notice that the two nodes, the nodes the capacitor is connected to, are ground and the output. And V naught is connected between the output and the ground. So they're the same connections, just opposite polarity. And therefore we have this relationship. So make sure you understand that. All right, so basically let's now go and proceed and find the solution for V of T. So I'm gonna this is a source-free circuit. Therefore, V of infinity is equal to 0 volts. Okay. Okay, so the next thing that we're going to do is, and we know that if we're given that initial value for a capacitor voltage is 4 volts. Okay. And so now the last piece that we need is the time constant. So to get the time constant, we basically have to look from the resistance and the counter. So I'm going to draw the capacitor as an open circuit. And notice that basically it only sees the feedback resistance. Why? Because this node is grounded. And this node has, if you remember, and the output impedance of an op amp under the I. So you can basically ignore, let's see, not clear, let's erase. So you can basically ignore all of this. And this RF, actually, is equal to RTH. So this capacitor only senses the feedback resistor, right? Because this node here is grounded, and because this node is grounded, it's not going to sense R1. Okay, so go ahead, Omar.
Could you go over again why we are only using RF and not like anything else
Yeah,
for RTH?
yeah, it's a really good question. It's one of the things that when I first taught this course, I had to sit with this. I had to sit with this for a while and figure out why. So I think the best way, though, is the best thing to notice is that this here is grounded, and this here is also grounded. And so there cannot be any current through this resistor. So there's no, this is essentially, it's pretend as if R1 is equal to 0, right? Because there's no other form of resistance. Basically, there's no current over here because of the ideal op amp assumption, and there's no current over here because this node is grounded, and so is this node. So I've kind of made a mess of it. So let me just. Yeah, exactly. Exactly. Thank you. I'm glad that that makes sense. Again, this thing, I remember having to stare at it for a while before it made sense. So the RTH is equal to RF, basically, is equal to 50 kilo ohms. All right. So now we have everything we need. Now we can write rather, our expression for V of t. And so should have also said that tau equal to RTH times C is equal to 50 times 10 to the 3 times 10 times 10 to the and the reason that we allow calculators on the finals because you're gonna have to. I'm not saying just to ease your mind. I don't think I've ever put a first order op amp circuit on an exam or anything like that. But you will need a calculator for some of the other calculations. So that becomes, let's see, I think that becomes half a second. So it's 500 over 1,000, so half a second. All right. So now we can write our full solution for V of t. So our our final voltage was 0. So we're just going to ignore this. And our initial was 4 times exponential negative 2t. All right. And so V naught of t is equal to negative 4 exponential 92t. All right, let me just see now if I can go to the next slide. Oops. Yeah, that's right. I got the looks very messy now. So okay, so indeed, and I have my solution here. So the final answer, which we just derived previously, is that V naught is equal to minus 4 times e to the minus 2t. And again, to solve that, we had to solve for the capacitor voltage and noted that the output voltage here is equal to minus the capacitor voltage. All right. Let's see. We're not going to get through this whole lecture, but that's okay. I'm comfortable with not covering every slide in first order op amps. I will, though, I'll present this problem and then I'll set you guys free. So this is an example of a step response. Right? It's a step response because we have a voltage source that is connected to the non-inverting input after time 0. Right? And we are asked to find the capacitor voltage V and the output voltage V naught. So let's first draw this circuit right before that switch closes, right? So we know that this is a step response, right? So our solution is going to have, our solution for V is going to have this form. So let's first find V and then try to convert that into V naught, right? So we need to find a time constant, the initial value of the capacitor V naught, and its final value V infinity. Okay. So basically, the first thing that we're going to cover, the first thing that we're going to solve for is the time constant. So for the same reasons as before, right, this capacitor only senses the 50 kilo ohm resistor. So the feedback loop of this op amp constitutes an RC circuit with a time constant of 50 milliseconds. So right away we have our time constant. And notice that before time 0, there's no input into the circuit. And therefore the initial value of V naught is just equal to 0. Right? There's nothing energizing this circuit before this switch goes from the open position to the closed position. Okay, so now let's look at after that switch flips. And this is where I'm going to try to draw, or I don't know how to draw. So let me just annotate this at least. So if the switch is closed, right? This is ground. Right? And so there's a voltage difference of, there's a voltage source of 3 volts that is connected in series to a 10 kilo ohm and a 20 kilo ohm. We're interested in this voltage here, V1, because that is the input to the non-inverting side of our op amp. And so this is, we have basically a voltage divider. Everything that I'm highlighting, everything I'm going to try to draw a dashed box around. Right. That's all a voltage divider. And so this 3 volts gets dissipated 10 kilo ohm and the 20 kilo ohm. So basically, this node here is sitting at 2 volts because 20 kilo ohms is 2/3 of the total impedance. Right. So from voltage division, the value of V1 is equal to 2 volts, which means that both assumption are equal to 2 volts. All right, let's move on to the clear the annotations. Okay, so just remember that V1 is equal to 2 volts here. So at steady state, so long after this switch is closed, the capacitor here is an open circuit. And so this circuit is just a non-inverting amplifier, right? So the gain of that non-inverting amplifier, if you remember, is 1 plus the ratio of the feedback resistor to the input resistor. So if you remember, if you had when we covered non-inverting amplifiers, the gain was equal to 1 plus RF over R1. Well, R1 is this resistor. Okay, so the gain here is just equal to 3.5. And the input is 2 volts. Let's remember that this input here is equal to 2 volts, 3.5. Okay, so a voltage of 2 volts, an input of 2 volts, with a gain of 3.5 means that the output at infinity, at steady state, is equal to 7 volts. Continue on.